Okay, welcome everybody. Happy Halloween. So the midterm this coming Thursday, I'll post it and you'll have access to it. It'll be essentially the same format as the last one, and GitHub issue about the review sessions. Thursday at this time is good. Tuesday at this time is there. It overlaps with the normal office hours. So if somebody wants to suggest a different time on Tuesday, then we'll do something at the different time. But I don't want to just cancel the regular office hours on Tuesday. Any questions about, let's see, here in a second there, I know there's a couple of questions about some of these problems, the practice problems that I handed out, so we'll talk about those in a second. But anything about question administrative wise for the midterm? Okay, then questions related to these practice problems. I'll just talk through, I think the questions were on all these first ones here about the perceptron hypothesis class. And I'll just talk through the answers to these first few here. And if, as I'm doing that, more questions arise, feel free to interrupt and ask questions. So problem number 3 right here, let H be the perceptron hypothesis class and assume there exists some H in capital H with the true output equal to 0. Then after a finite number of iterations, the perceptron learning algorithm is guaranteed to output a hypothesis G satisfying that E sub n of G equals 0. The perceptron learning algorithm, again, the PLA, one of the properties about that is that it will only converge for a linearly separable hypothesis, or for a linearly separable data set. And if the data set is not linearly separable, then the PLA will run forever. There's this alternative to the PLA, the pocket algorithm, which is what you use if the data is not linearly separable. Here it's not mentioning, it doesn't explicitly say anything about linearly separability. It doesn't use those words in this problem 3 anywhere, but you can infer from the given information about whether the data set is or is not linearly separable. In this case, because I say assume there exists some H in the hypothesis with the E out of H equal to 0, that means the data must be linearly separable. This sentence right here implies linear separability. The reason for that is because it is the linear hypothesis class, the perceptron hypothesis class. And if we get 0 outputs, 0 true error, then the data must be separable. That's the definition of separable, is that there's a hypothesis in this hypothesis class with the error equal to 0. And so I don't explicitly say anywhere that it's separable, but you need to be able to infer that from the given information to answer that this is going to be true. Because it's separable, it will terminate in a finite number of iterations. And we have a formula for what those number of iterations are. It's related to the diameter of the data set compared to the margin of your hypothesis. But we don't need that formula just to know that it's going to be a finite number of iterations. Slight subtlety about this is that from the perspective of the learning algorithm, again, the learning algorithm doesn't have access to the true error anywhere. It doesn't have access to E out. So really what we care about is whether the training data set is linearly separable. So what we care about, what determines whether PLA will converge or not, if E sub n of H equals 0. So if the in sample error is equal to 0, that is the equivalent condition to PLA converging. And it happens to also be the case that if the out of sample error is 0, then the out of sample error is like the in sample error, just with infinite data points as the number of data points goes to infinity. And so the in sample error is like a finite subsample of the out of sample error. And so there's no way that this here can be non-zero if this thing up here is 0. So a lot of things that you need to connect together to get to the right answer for this problem. Yes.
Does the PLA converging necessarily mean? Okay, well, so the PLA converging doesn't necessarily mean that the out of sample error is 0.
Question is that here I wrote this arrow with a double implication, and does the implication go both ways? And the answer is that the implication does in fact go both ways.
So I meant the out of sample error, not the in sample error. So if the PLA
pause that. Sorry? Just pause the question for a second. So the reason that this this arrow goes both ways is that what the PLA algorithm says, if you go back and look at the pseudocode, is that it says always take one particular data point that is not classified correctly, and you loop until all the data points are classified correctly. So if the PLA converges, it means that all the data points are classified correctly. Since it's using a linear classifier, that implies linear separability and the EN converging. But then the actual question was, does the E out equal to 0? Or does PLA conversion guarantee that our out of sample error is equal to 0? And here the answer is no. That if we were to draw a very simple data set like this with just 2 data points, then there are many possible separating hyperplanes that the PLA might give us. Probably the one we might hope to have is this one, like this, that has the largest margin between the positive and the negative point. But the PLA could also reasonably give us this one or this hyperplane. The PLA makes no guarantee about that it uses the best possible separating hyperplane in any sense. It just guarantees that it's going to give one hyperplane that separates the data points. And so depending on what our actual data set is, if our actual data set, so the blue points here drawing being things in the out of sample data, if the out of sample data looked like this, and the PLA returned this solid red line, then the out of sample error would not be 0, even though the in sample error is 0. And so that's what problem 4 is essentially asking down here, that there's 2 changes in problem 4. The first change is that up here, the in sample error is equal to 0, instead of up here was the out of sample error equal to 0. We use the fact that the out of sample error up here was equal to 0 to imply that the in sample error must also be equal to 0. That remains true. And so if either of these 2 things is the case, then the PLA will converge. But the other difference is down here, the out of sample error. This out of sample error is not guaranteed to be 0 by the argument that we talked about up here. So the algorithm will still converge in a finite number of iterations, but the hypothesis is not guaranteed to satisfy this. So we get false for number 4. Did that answer your question?
Yes, thank you.
Kieran, did that answer your questions from before that I cut you off? Okay. Anybody have other questions on these 2 problems? Okay, so number 5, very similar to the previous ones, just worded in a very different way. So H again, the perceptron hypothesis class. There is some H in H with E sub n of H equal to 0. And then the PLA will terminate. Again, synonym for converge. And so this one is going to be true. This right here is the statement that it's linearly separable. So lots of different ways that all of this information can appear inside of problems, and you have to be able to connect all those different things together. Any questions about anything related to the midterm? Question? Number 11. So H1 and H2 are two hypothesis classes where H1 has a larger VC dimension than H2. And we have G is inside of H1, G2 is inside of H2. And then the Hoeffding inequality predicts that the test error of G1 to G2 is less than the test error of G2 to G2, or the test error minus the output error. The Hoeffding inequality, so the key thing about the Hoeffding inequality is that it's related to finite. Some things have to be finite samples somehow. So the information about the VC dimension right here provides us no additional information about anything that can be related to the Hoeffding inequality. No additional information. It's basically just a distraction. And we used the Hoeffding inequality in two places for two purposes. One was to bound E in minus E out for finite. Size A less than, for finite hypothesis classes, bounding our generalization error. That was one purpose of the Hoeffding inequality. And we said that this isn't like a very good use of the Hoeffding inequality because most hypothesis classes that we care about are actually infinite dimensional. And that's why we spent a whole bunch of time talking about the VC dimension, is because the VC dimension gives us a tool for bounding the generalization error on infinite hypothesis classes. We know that this isn't the sort of like thing that's going to be useful in this particular problem, though, because it's not talking about comparing E in and E out. It's talking about comparing E test and E out. So this is not the use case of the Hoeffding inequality that we care about. The other use case of the Hoeffding inequality was for bounding E test minus E out. So that's use case 1 in blue, use case 2, bounding E test minus E out. But this bound didn't depend in any way on the size of our hypothesis class. All that it depends on was the number of, only depends on number of data points in the test set. Data points in the test set. And so what Hoeffding's inequality actually predicts is that the bounds on those two things are going to be the same, not that one bound is going to be less than the other bound. In general, the test set, whether you're how good of an estimate your E test is of E out, that has no, what hypothesis class you're working with has no impact on the quality of this difference right here. The only thing that impacts the size of this error, the quality of the estimate of E test compared to E out, the only thing that impacts this is the size of the test set. Even if you have a really big hypothesis class, it doesn't matter. The size of the hypothesis class is what determines the bound between E in and E out.
So what if you true E in minus E out?
So the question is, what if it was E in minus E out? So what if it was asking about the generalization error instead of the instead of this? We don't have a name for this, but the difference between the E test and E out. The question is, what if it was asking about E in minus E out? And the answer is that it's still false in that case, because in order to use the Hoeffding inequality, we need to know something about the finite size of the h's, and DVC being finite doesn't actually imply that the h's are finite. So we would not be able to use Hufting's inequality to bound E in minus E out, only giving this information right here. We have another inequality, which is not based on Hufting's inequality, which I've been calling the fundamental theorem of statistical learning, that bounds En minus E out based on the VC dimension, but Hufting's inequality doesn't do that.
So, just to clarify, in this case, the E test, that's like, it's separate from E in, but it's not necessarily E out because it's not a finite number of data points.
Yeah, so E in, the in-sample error, is using data points that may have impacted our choice of G right here. And so we can't use Hufting's inequality on that because they're not independent of each other. E test is on, the definition is very similar to En in that it's on a finite set of data points, but those finite set of data points are not used at all in training. And so they're all independent of each other. And so because of that, Hufting's inequality can be used to bound that quantity.
Yeah, and then E out is just it.
And then E out is the limit of E test as the number of training points goes to infinity. So yeah, what's going to be tricky on the true false questions on this midterm is just very subtle differences in the formulas up here, like just this word test to in, or changing the direction of an inequality can have huge impacts on what sort of reasoning you need to do and the final output of what you should write over here. Again, the only situation where we've talked about open problems for this midterm is the runtime of binary classification. That's an NP hard problem with the 0-1 loss, and anything that's just on statistics guaranteed not to be an open problem. If it's on runtimes, then you might have to think about whether it's open or not. Okay, new material for today. So where we're going is, that's not, here we go. So inside of this applications model zoo is where you'll find the PDF that is our notes for today. And the purpose of this set of notes is basically to figure out what can we do with all of these different models that scikit-learn or any other machine learning library has implemented. If you look over here, so this, again, the scikit-learn documentation. Under supervised learning, every one of these links is essentially a different model that we can pick from. And if you scroll through this, you can see there's a lot of different models that we could pick from. There's like 60 or 70. And in order for us to determine which one of these models we should use on any given problem, there's a number of ways that people do this, but what we're going to do is we're going to talk about the VC dimension of all these problems or all of these models, and then we'll be able to use our existing tools to determine whether a model is too complicated or not complicated enough for a particular problem. None of this information from this notes packet is in the textbook at all. We're very close to being done with the textbook. There are some citations throughout this notes packet, but you're not going to be responsible for any of the material inside those citations. There's going to be a lot of text in this note packet, which is, I don't know, somewhat unfortunate in that it might be the case that it's easy to just kind of glaze over and stop taking notes or things. But I wanted to make sure that the text was in here, that you didn't have to copy off some very important theorems about things, since it's not easily referenced. Okay, so this picture right here comes from the scikit-learn documentation, and it's a very common sort of picture that you'll see when people are talking about different types of models. On the top axis up here, these labels, each column is a different model. This linear SVM right here is the only one that we have talked about at this point, that the linear SVM uses that linear hypothesis class. And every model is a combination of a hypothesis class and a algorithm for selecting a hypothesis. And it uses the hinge loss with either gradient descent or stochastic gradient descent to select the hypothesis. So we didn't spend a whole lot of time talking about the hinge loss. That we focused on the logistic loss, which would be logistic regression. But the hinge loss and logistic loss are basically the same. So you basically always get the exact same results. And the generalization properties are the same since it's the same hypothesis class. Each row over here is, this leftmost column is different data sets. This one, you have sort of like a moon shape with this blue and this red one, so it's not linearly separable. So you can look down here and see that a linear hypothesis class is not going to be good on this data set. This, zoom in a little bit. The dark blue lines are things that are more, the model's more confident of being blue. The red area over here, the model's more confident of being red. The decision boundary is between the red and the blue lines, like the spot where it's deciding whether something is red to one side and blue on the other. And you can see that there's going to be a lot of guaranteed misclassifications here because a linear model is just not good enough. And so we've seen these sorts of data sets. This has been one of the sort of prototypical ones. The circle data set I've been drawing a lot as a counterexample to the linear model. And then here's a linearly separable one down here. And through the notes today, we're going to talk about, and probably won't finish it today, but we're going to talk about all of these other models at a very high level and why they have more complicated decision boundaries and how you should use the VC dimension to select which one to use. Any questions at a high level? Okay. Again, all this material not going to be on the midterm, but tried to schedule this kind of during this intermediate spot before we have the next midterm, because it is, I think, helpful review to just think about why do we care about all these VC dimension facts that are going to be on your midterm. The VC dimension facts are going to help you determine which one of these models you'll want to select. Okay, so the notes are divided into sections here where each section thinks about different classes of models. And the first class of models is these linear or quadratic models. If I come back over here to the documentation inside of scikit-learn, one of the things that you are expected to be able to do is to figure out which one of these models are linear and which are quadratic, and which don't follow any of those patterns, something else. So anything under linear models, easy to figure out is a linear model. But not all linear models are in that linear model category. These linear and quadratic discriminant analysis, either linear or quadratic, support vector machines. These are all linear. Stochastic gradient descent, also going to be used only on linear things. And way down here on naive Bayes, these are all either linear or quadratic, depending on how the hyperparameters are set. Everything else is something else and doesn't apply to this part of the notes. But the idea of these linear quadratic models is they're called this way because all linear models use the hypothesis class of half spaces. So they all use the same linear hypothesis space. And all quadratic models use half spaces with a second degree polynomial kernel. That's why they get the name of quadratic models. And so we know what the VC dimension of all of these models is. It's either theta of d if it's linear or d squared if it's quadratic. And so we know the generalization errors of all of these models using our VC theory, using these results right here. The only difference between these models is how the actual hypothesis is trained. And in particular, all of them make different assumptions about the underlying data in order to make training easier in some sense. But logistic regression, or SVMs, these two models right here, are essentially always give the best performance. And it's what people, at least today, always use in practice, because these models directly optimize so logistic regression and SVMs directly optimize or optimize our E sub n value to make it as small as possible. And the thing that we care about, E out is always can be broken out into, that's a less than or equals right here, less than or equal to En plus En minus E out, that difference right here. And this has the same bound for every model. Same for everything. This right here is smallest for these two, logistic regression and SVMs. So E out is the smallest for these. And again, that's what everybody in practice uses. If you're using a linear or quadratic model, everybody will always use these days either logistic regression or SVMs. So that's like, I don't know, 20 or 30 if you look into the documentation for scikit-learn, 20 or 30 of those models that if you can just throw out the window, you should never consider them. If you see somebody else using them, then you can suggest try logistic regression, you'll probably improve your results. Any questions about that argument, that line of reasoning?
Sorry, like, there are other like different models that also also can directly optimize EN, right? The PLA, is that not what the PLA does?
Yeah, so the question is, how does PLA fit into these things here? The answer is that, so PLA is only working on linearly separable data, and it's really only useful for theoretical discussions because no real world data set is going to be linearly separable.
Yeah.
There's that pocket version of the PLA, which can work on nonlinear separable data. That has the disadvantage, though, of its has the exponential runtime.
Yeah.
So again, on real world data, it's just not going to converge to a good result.
Right.
So yeah, I guess with the exception of PLA and pockets, none of the other algorithms listed in scikit-learn are optimizing this, and we don't use those two algorithms for those computational reasons.
Okay, and then why exactly is En minus E out is going to be for everything?
That this is bounded using our VC dimension theorem. So that is equal to O of square root dVC log n over n. And because these all have the same hypothesis classes, same hypothesis class, implies the same VC dimension. And we didn't exactly talk about this before, but this bound is tight. It can't be improved. So none of these other algorithms, none of these other training methods that select a different hypothesis, they don't have better bounds than this. They all have the same exact bound. Okay. So quick aside right here. A moderately common sort of interview question is to say, take something like the naive Bayes algorithm and explain why it is not a good algorithm to use or what the assumptions are and why those assumptions are violated. We're not going to talk about that in this class at all, that our discussion is going to stop just at the fact that naive Bayes is quadratic and doesn't directly optimize EN. So it would be better to use logistic regression with a quadratic kernel, and you'll get better results. So example problems, problem 1 down here. So a colleague is using quadratic discriminant analysis. Because it has quadratic in the name, you can guess that it is a quadratic hypothesis class. And so the VC dimension, dVC, will be theta of d squared. I specifically said here a colleague is using quadratic discriminant analysis and not you are using quadratic discriminant analysis, because you all should prefer using logistic regression instead of these other algorithms. And if they're using this algorithm, then provide a simple suggestion on how they could improve their classification their classification accuracy in the following situations. So the first here is that they are overfitting. And we talked about before, we have this chart or this graph that model complexity on the x-axis down here. And there's a lot of different versions of model complexity that we've talked about. The main one that we've talked about is the VC dimension. That's the one that'll be useful for us right now. Last class time, we also talked about L2 or L1 regularization. But for our purposes right now, it's the VC dimension that's the interesting one. And so this is high model complexity over here. This is low model complexity over here. And if you have a low complexity model, then your E sub n value is decreasing like this. You have high training error when the model complexity is low. Making a more complex model makes EN go down. You have your generalization error, EN minus E out behaves like this. And we have the specific bound based on the VC dimension about how EN minus E out behaves. And what we're really interested in, again, is the sum of these two things. E out over here. And what's important about this problem is, so it's saying that you're overfitting. So which region of this graph am I in? Am I on the right-hand side or the left-hand side?
Right.
Yeah, if we're overfitting, then our model is too complex. So this region over here is the overfitting. And so the thing to do is to reduce our VC dimension somehow. So we need to reduce the VC dimension. And that means, since we're using a quadratic hypothesis class, let's go to a linear hypothesis class. And if we looked through scikit-learn, the documentation, we would see that there is, in fact, a thing called linear discriminant analysis, which if they really wanted to continue using discriminant analysis, they could use linear discriminant analysis. But I would still probably prefer just logistic regression with no feature map. If this were a test question asking what to do in this situation, either of these answers, linear discriminant analysis or logistic regression, would be a fine answer to this problem. If you were being interviewed by somebody and they were saying their company is using quadratic discriminant analysis for a particular problem, then I would suggest going from quadratic discriminant analysis to linear discriminant analysis, since that's closer to what they were already familiar with. Any questions about this problem? Leave this up for a little bit more as everybody's finishing writing stuff. At a high level, this is so on this problem, I drew out a lot of, I guess, sort of showing my work, showing my reasoning sort of things, drawing out this model complexity curve. But this curve right here is something that all practicing data miners just have burned into our memory. And so we would just, like if I'm talking about this with people, I would say, oh, quadratic discriminant analysis, model complexity too high, that's why you're overfitting. And so let's find something with a simpler complexity like linear discriminant analysis. And not draw all these curves. Okay, the second problem down here, the training error E sub n is large. How would we go about fixing that? This is sort of the opposite problem that we had before. That we said we were overfitting if the generalization error is really high. En being large, another more succinct way of saying that is that we are underfitting. And I'll draw that with the double arrow sign, because that's really the definition of underfitting, that you're on the left-hand side of the curve above, that your model complexity is too low for the problem, so your in-sample error is too high. And so how should we adjust this? Well, we need a more complicated model. It turns out there is no more complicated version of discriminant analysis. There's nothing above quadratic. We could consider applying a feature map like the polynomial applying the polynomial feature map to increase the model complexity. These feature maps that we talked about before, we talked about them in the context of logistic regression, but you can use them on any problem. It's just sort of like a pre-processing step that you do before you would pass it into the library that you're working with. And so if we, for whatever reason, wanted to continue working with the quadratic discriminant analysis, this would be the choice thing to do. So that'd be the first option. The second option, though, the thing that I would definitely do first is just replace. So QDA for quadratic discriminant analysis with logistic regression. Logistic regression actually optimizes E sub n. And I'll just call that LR. LR directly minimizes E sub n, and so our in-sample error likely to be significantly lower. Thoughts?
We just regress technically made the model class.
Oh yeah, so good question here. So I had quadratic discriminant analysis up above. So I was using a quadratic hypothesis class. And now we're saying go to logistic regression. Logistic regression has a linear hypothesis class. And so you're right that I was implicitly saying use logistic regression with quadratic kernel. That's what I was thinking in my head, but I forgot to say that part out loud and write it down. That will make sure that we're using the same hypothesis class. So the generalization error will essentially stay the same, and then minimize the E sub n. Excellent points. Any other questions on these linear quadratic hypothesis classes? Okay, so let's get a little bit more interesting now with a multi-layer perceptron hypothesis class. The multi-layer perceptron is an example of a neural network. And these terms often used synonymously with each other. But libraries will basically always say that it's the MLP will be like the name of the function that does the training, and people will just talk about it in words using neural networks. Let's see. At a high level, when people first introduce people to neural networks, or when people are trying to describe neural networks, they often use like motivated language, talking about how like comparing to a brain somehow. We're not going to talk about neural networks in that way at all because it's not a useful analogy, and people who are actually practitioners that are using this stuff in practice don't think that way. So instead, I'll try to describe to you how actual practitioners think about these multi-layer perceptrons neural networks, and the sort of intuitions that we actually use when deciding when and how to use them. So this first part up here is a little bit of review. That this is our class of binary half spaces right here, or the perceptron hypothesis class. And we've talked about that if you're applying a feature dimension, or a feature map, changing your dimensions to this D prime, then this is what your half space hypothesis class is going to look like. And everything that we have talked about so far, so when we're using logistic regression or SVMs or whatever we're using, this phi function is something that you have to decide on in advance. So up here, this is everything that we've done so far. And the key idea is that phi is selected in advance. Well, since we're talking about like machine learning, somehow learning functions from data, this phi function is just another function that we could learn from data. And the original motivation of these neural networks, of these multi-layer perceptrons, was that, okay, let's not just learn this function from data. Let's not just learn our H right here from data, but let's also learn our feature map from data. And so this equation 5 right here describes how that's done. This phi sub x, or phi of x, has this form right here. This W1 is a matrix, has shape D prime by D. And so W prime, D prime by D for W1 right here. X has shape D. And so the final product of W1 and X will be just a D prime vector. This goes from D to D prime, r to the d to r to the d prime, which is the same as what we had before. It's just parameterized in this way. This sigma function right here is commonly called an activation function. It is a function over scalars from r to r, and we apply it element-wise to this particular vector that we get from w1 times x. So element-wise to this right here. And then besides just learning this W from data, we'll learn the W1 matrix from data as well. And that will learn our feature map. This is the formula for a one-layer perceptron, has just a single one of these W1s. A multi-layer perceptron with k layers will have be phi to the k up here, where it's recursively defined that, okay, if we learned, like maybe I want to apply another feature map up here, I'll just apply this phi to the x, and you do that recursively for every layer. Each layer is going to have a different weight matrix associated with it, and learning those feature maps. It's not a very intuitive thing at all about what's going on. The important thing will just be that if you have all of these weight matrices, so we have X, and then there'll be like an A1, sigma. I'm unraveling this recursion right here, times an A2 with a sigma, times an A3 with a sigma. And we'll go up to A4 with a sigma. Each one of these matrices has to have dimensions associated with it. So X right here, calling it D. A1 right here will be D1, D0 by D1. This corresponds to A, this corresponds to X. A2 right here will be D1 by D2. A3 up here, D2 by D3, and A4 up here, D3 by D4. All of these dimensions of these matrices just need to match each other. And so this D0D, just called the input dimension, same as what we've always called it. This D1 right here, dimension of the first layer. This D2, dimension of second layer, and so on, dimension of third layer. And then this output dimension over here also equal to D prime. And when we're specifying like what is the shape of our neural network, or what is sometimes called the architecture of our neural network, what is the hypothesis class that our neural network is learning, what we have to specify is all of these D sub I values. And scikit-learn, the function that does this, just has you input a list, which is the list of these D sub I values. We're going to take a look here in the next page about some results on the VC dimension of those results on the VC dimension will give us some insight onto how we're going to select these values to make it appropriate for our problem. But before we do that, we'll do visit another web page that'll give us a little bit more maybe intuition about what's going on here. Before we do the intuition, any questions on the notation? No? Good question. So the question is, how does D prime relate to the VC dimension? The answer is that for the multi-layer perceptron, we haven't seen that yet, that it's going to be very complicated. For standard logistic regression, where this phi function is fixed in advance, then DVC equals theta d prime in this case up here. So the for the polynomial kernel, for example, increasing the size of the polynomial makes the d prime be larger, increases the DVC, makes us able to support more complicated functions. Good question. Any other questions about notation? Okay. This note at the bottom. So the multi-layer perceptron, special case of neural networks, TensorFlow, PyTorch, common libraries from Google and Facebook for doing really complicated things with neural networks. Scikit, though, lets us use this particular form of neural networks. We'll get into TensorFlow and PyTorch in the coming weeks for those more complicated things. But I bring it up now because there's this interesting website down here which lets us visualize these shapes of neural networks a little bit, maybe more intuitively. So this is just following that link. I'm going to, on the left-hand side, there's different data sets that we can try to fit with a neural network. Here, their default neural network has 2 hidden layers. I'm going to start by reducing that down to 0 over here. If we have 0 hidden layers, then this is 100% equivalent to logistic regression or support vector machines. And so we know that, so these are our 2 input features over here, X1 and X2. We know that this type of data set over here, this circle data set, is not something that we can fit with just logistic regression. And if I press this run button over here, the run actually tries to do the training. And we can see that as it does that, here appears the test loss and the training loss. They're both really large because you just can't fit a linear hypothesis to this hypothesis class or to this data set over here. One of our original tools for dealing with this is to modify the features of our data set. This x12 right here is x1 times x2. x22 is x2 times x2 like this. And if we do that, that's like applying the this one here too as well, x1 times x2. These are the adding this is the polynomial kernel of degree 2 onto this data set. And we've seen that the polynomial of degree 2 can in fact fit this data set over here. So one way of fitting this data set is by just modifying the features over here that we're using, adding more features that are somehow computed from this data. The idea of the neural network is that we want to compute these features for us automatically somehow. So I'll add a hidden layer that's going to do that. And so this hidden layer right here, this is what in D1 is what our notes is referring to. It's the size of the hidden layer. There's a matrix over here that maps from these to these. And if we train that, then we can see that it's sort of able to get a kind of quadratic-ish shape. It's getting a little bit better, but still not great. But if we add more things to this hidden layer over here, run that, then it's going to eventually be able to kind of get something that is not exactly perfectly circle-ish, but pretty good, pretty low training loss and pretty low test loss. The important thing about this visualization, comparing back to our notes, that here the number of these hidden layers, we come back here, The number of these hidden layers is the number of these matrices that I've called A1 up to A4. This one here would have 4 hidden layers. And then these D1s right here, D2, D3, those correspond to the number of these boxes here in this visualization. So we have more layers if we wanted in this visualization. And maybe that'll do better, maybe it'll do worse. In this case, it seems to do a little bit better, a little bit more round over here. There's a lot of, so all these different things that you can change, like the number of hidden layers or the number, the size of each hidden layer. These are all hyperparameters, again, of our model. And there's a lot of these different hyperparameters that you can tune about your multi-layer perceptron. So the particular dimensions of all of your parameters that you're learning is the most important one. But another one here is this sigma, this activation function. The main important thing for that activation function is that it has to be nonlinear in order for you to get any benefit out of these hidden layers. If you use a linear activation function like this, run this, this is still going to end up being a linear hypothesis class. It's not, you can't even really see the separation very well over here, but up here you can see that it's not fitting the data well at all. 0.5, 0.5. The most common activation function in use these days is the ReLU activation function, but you get pretty similar performance no matter which one you're using. Any questions so far? Okay, it's all very high level, very abstract. Maybe we're going to get even more high level and abstract here on the next page, but the next page is going to be the important part, that what we're going to need to know about multi-layer perceptrons is how can I estimate the VC dimension of the particular model so that I can know how I should adjust these hyperparameters. Should I make these D dimensions bigger or smaller? Should I add more layers or take layers away? And we'll need to know about the VC dimension in order to do that. Let's see, the first thing before actually the VC dimension, this idea of universal approximation. We've talked about that with the polynomial kernel that we said with the polynomial kernel as the degree of the polynomial goes to infinity, our training error goes to 0. This is something that you need to know for the upcoming midterm, that this property about the polynomial kernel can approximate any function as long as you're high enough degree. But again, the downside of that is that your VC dimension goes way up. As the degree goes to infinity. The multi-layer perceptron is probably the most famous of, or its universal approximation algorithm is the most famous of universal approximation algorithms. And that's that for a one-layer multi-layer perceptron hypothesis class, as the D1 value, as the number of internal nodes in that multi-layer perceptron increases, the training error goes to 0. So in particular, what you need to know is what do you have to increase? What to increase in order to drive the training error to 0. And that's the width of the neural network. You only need one depth, one recursion in the definition, but in order to make the training error go to 0, you might need a very, very large width. It's that width that'll go to 0. In order to talk about the generalization error now of the resulting model, we need to talk about the VC dimension. And the VC dimension of neural networks is extremely complicated. So there's two theorems down here that we're going to discuss about. We'll talk about them in turn. You're going to have to memorize these facts about the VC dimension of the multi-layer perceptron. And again, these are going to be the facts that you'll be appealing to when you think about how should we change the structure of our neural network, and should we even use a neural network in the first place. You'll be using these facts to understand what will the generalization error of the model be. So the first fact, which is the simplest, is that the VC dimension of, doesn't matter how many layers you have here, if you have the identity function, then your VC dimension is guaranteed to be theta of D. So I mentioned that previously in that visualization over here, that if you have the identity linear activation function, it doesn't matter how you adjust things over here, you'll see that you're always going to get this training and test loss of 0.5. Doesn't matter what you change over here, you'll always get that same result over here. You can't make the network any more complicated unless you change this activation function. There are no reasons in practice why anybody would ever use the identity activation function. With a VC dimension, that where sigma is the sign activation function. So this is the way to think about that is that it's like using a perceptron to estimate all of your features. Each perceptron is estimating the features of the next perceptron in the next layer. This is, and that's the very first activation function that people were interested in. That's why the name is the multi-layer perceptron, because it's the perceptron that's iterated over again. And again, the sign is the loss function for the perceptron. Then our VC dimension is this thing right here, O of E log E, where E is defined in this complicated way up here. I'm going to go up above here to remind us what all the definitions are and talk about what this formula is doing when we're up above on the previous page where we can see the definitions. The basic idea of that E value, do this in orange. The idea of E, the intuition of it, is that it's the total number of parameters that need to get learned. And that formula that I have down there is just the total number of parameters that get learned. The total number of parameters is, if you actually consider these things as numbers and these x's as multiplications, it's all those things multiplied together. The A4 is a D4 by D3 matrix. So there are D4 times D3 entries in the A4 matrix right here. A3 is a D3 by D2 matrix. So there are D3 times D2 entries in the A3 matrix up here. The reason that formula is complicated is because the internal dimensions, the dimensions of all these internal layers, these things in the middle between D and D prime, they get repeated twice because they have to match the dimensions of A3 and A4. This D3 will be repeated twice. And so we'll go down and look at the formula again here in a second, but we'll see that these internal things are squared. These D4 and D, the things on the very outside, those things are not squared because they only appear once in this chain of matrices. So the intuition behind here again, so D prime D, these only appear once in that chain of matrices. And so they only appear one time, both in the formula and in the dimensions of the parameter matrices. These over here, though, they appear twice in both locations. So if you, for example, you have a neural network and you want to double the VC dimension, you cannot double the size of one of these internal layers, because if you do that, you'll actually be multiplying E here times 4. Instead, you would be doubling one of the first or the last dimensions to double the value of E, and in turn, double the VC dimension down here. Are there any questions about what this E value is equal to, any of that notation? I realize that it is extremely notation dense and intuition light. But these are the actual things that people, the way that people reason about things. So this here is, again, specifically with the sign activation function. Another common activation function is the hyperbolic tangent, or the sigmoid activation function. And here we actually, so there's an open problem. We don't know how to compute the VC dimension of that particular multi-layer perceptron. Instead, all we know is that it satisfies these two bounds right here, that it's either, it's at least E squared, and it's less than V squared E, where V is just the products of the D's without the duplication of the inner terms. So this is open problem, finding the exact to calculate the VC dimension. One thing that you can notice, though, is that the VC dimension of the tanh multi-layer perceptron, no matter what, is guaranteed to be bigger than the VC dimension of the K-layer perceptron. This down here, omega E squared, guaranteed to be bigger than O of E log E. And so if you're overfitting up here, overfitting with the sign activation function, you would never switch to the tanh activation function, because then you'll just overfit even more. Any questions about this theorem 2 and the statements of these results? Okay, all these are taken from this other textbook, Understanding Machine Learning from Theory to Algorithms. I put a PDF copy in the GitHub repo for the class if you wanted to take a look at like where these things are actually coming from. But you don't have to. These facts right here are the things that you need to actually know in practice. If this were a machine learning course, then we would be talking about like the proofs behind why these things are the way they are. This is the sort of thing that machine learning people care about, is proving the VC bounds on things. But the data mining perspective on this is that we don't care about the proofs of this. We just care about how to use them for things. And so we use these sorts of formulas in order to determine which model to select. In practice, again, I mentioned that the ReLU activation function is the most popular one these days. And we also don't know the exact VC dimension of the ReLU activation function. We just know that it sits somewhere between these two things up here. K here is the number of these hidden layers, the number of iterations we've done on that phi function up above. So the depth, the height of your neural network, as that increases, your VC dimension is guaranteed to be increasing. And there's a very sort of trivial dependence difference over here, but it is something that we don't know. There's also open problem. Okay, so real quick, jump to practical like applications related to this. That this is all make it a little bit more concrete. down to problem 2 over here. This part 1 here says that, so you're training this MLP classifier from scikit-learn model, and our activation function is the ReLU activation function, and our D is 1000 right here. And this hidden layer sizes hyperparameter tells us what are all the D sub I values. This is the list of the D sub I values. And so we have 2 options of these D sub I values that we could pick from. This list of all 10s over here, or this list that contains only 100 over here. And in order to determine which one of those is going to be most likely to overfit the data, we would want to compute the VC dimension of both of these. So VC dimension of A, VC dimension of B, and our formula, again, this is the ReLU activation function. So we come back up to this theorem right here, EK, essentially log E after here, probably won't matter for us, that it's equal to O of EK log E, like that. O of EK log E, like that. And the K value for choice A, K is the total number of layers you have. So K is equal to 3 up here. K is equal to 3 down here. The K value is equal to 1 for this bottom one. K equals to 1. The E value was the product of all of these things together. Here, this 10, that's the D1, that's the D2, that's the D3 right here, or the also the D prime, the output dimension right here. And so here, so it's D times D1 squared times D2 squared times D3 if you go back to that formula and compute it for actual 3. So that's 1000 times 10 squared times 10 squared times 10. Down here, this is going to be, we only have this value right here. That's going to be equal to the D prime, the number of features that we're going for. And so K is equal to, K is equal to 1. E is going to be equal to the D times D prime, or the D1 value right there. It's equal to 1000 times 10. And you can see that this bottom number, VC dimension, is going to be much smaller than this one up here. And so B, so it said more likely to overfit. So this one's more likely to overfit. More overfit and less overfit. And so depending on whether we're overfitting or underfitting our data would determine which one of these 2 choices we're going to make. And just by looking at these numbers up here, it's very unintuitive, unobvious what you should be doing with them. But these admittedly very complicated VC dimension formulas that we have above give us a tool for actually determining that. So that's the motivation. Being able to answer questions like this is the motivation for having those theorems above. Question?
For B, why is it 1000 times?
Sorry, that 10 should be 100. It should be that value right there. Thank you. It's a good stopping point for us for today. If anybody has questions about this or midterm stuff, I'll be available after class. Happy again to do the extra office hours on Thursday. If you want additional ones before then suggest a different time on GitHub.